okay? So, all right. So we're going to touch on programmable controllers this week. So it's kind of bleeding into PLCs a little bit. But last week, I know you weren't here for the lecture, but we went over VFDs, and you know what a VFD is, a variable frequency drive. So this week's lab, we're going to be using a PLC to control that VFD. So that's what we would be doing. But let's just go over some back info on PLCs. So they were designed to solve the problem of automating larger and more complex control systems. So they were developed to eliminate individual control relays and timers by consolidating them into one unit that could be programmed and reprogrammed as required by the application. And so PLCs led to the development and usage of a higher end control system that could tie the technologies of PLC industrial control technology with PC technology. And so there are 3 different types of control systems or programmable controllers that you would see. And those are PACs, which are programmable automation controllers, PLCs, which what we always mess with, and PLRs, which is programmable logic relays. All 3 platforms are designed to have digital and analog controls connected to their input section and their output section control electrical loads. And it makes it easier and safer to control, program, and monitor small or large systems. So this is just like a little diagram, and it was like explaining the system requirements compared to the size of the system. So some system control sizes would be number of inputs and outputs, unit expandability, and type of input. So discrete, analog, and motion. We'll go over those in a minute. And then system requirements, expandable needs, network control, monitoring, and integrating software and hardware. So what are some examples of systems PLCs might be used in, do you think? Like everyday or in industrial settings, or what are some things you think they might be used in?
Like factory work?
Yeah, I mean, they could be in like a factory or like just in everyday life. So, like they could be used in traffic lights or whatever. You know, you don't think of it like that, but they are. So, like, here's some examples. So, it would be conveyor belts, traffic lights, elevators, roller coasters, wind turbines, car washes, etc. So, you know, you don't think that, like, when you're going through a car wash, like, oh, this might be being controlled by PLC, right? All right, so they allow machines to have their own unique capability using standard hardware. And an example can be they can be used to control the speed of a production line, divert production to other lines when there's a problem, make product changes, and maintain documentation such as inventory and losses. All right, so there's different parts of manufacturing, and so one of those would be discrete parts manufacturing. And they produce durable goods such as cars, washers, refrigerators, and tractors, stuff like that. So that's discrete parts manufacturing, okay? And all machines, such as machines that can bend, drill, pinch, grind, and shear metals, they can be automated with programmable controllers at those plants. So, you know, like if you was working in a car plant, like there's plenty of people that have graduated from here that, you know, are PLC programmers and stuff like that at different car plants, chicken plants, whatever you can think of. And then process manufacturing produce consumables such as food, gas, paint, paper, and chemicals, etc. So they're more like the, goods that we would see every day in our lives or whatever. So most processes require systems to blend, cook, dry, separate, or mix ingredients. All right, so PLCs are primarily designed for the harsher environments found in industrial applications. They control circuits with many inputs and outputs with individual input and I/O modules that are designed to be connected to 8, 16, 32, or 64 devices. Like you're kind of touching on that right now in your PLC class, aren't you? Oh, but you know what I'm talking about then, so you've touched on this. So individual modules can be added or grouped together in a 4, 6, 8, 12, or more units within a rack, but they can be expanded to control over 1,000 IOs, right? All right. So smaller PCs, aka standalone PCs, do not allow for interchanging or adding modules to them. So you can't add anything to standalone PLCs. I guess they're just too small. Like you can't add an excess of information to them. So here's just something that I added on here. So what type of manufacturing is a soft drink bottling plant an example of? We just talked about it just like 3 slides ago. So there's 2 different types of manufacturing we talked about. Process or discrete. So what would a soft drink? So a soft drink is what? A consumable? So what kind of manufacturing do you think that would be? Process. So that would be process manufacturing. So what would an example of a furniture plant be?
That would be
Discrete. Yes. So you can kind of get the gist of it, like process or consumable goods. So just try to remember that because it might be on a quiz or something. All right. So basic control requirements. This would just be like the control requirements of any system that you see out in the field. So that would be controlling circuit outputs based on circuit input conditions, digital inputs connected to their input section, analog inputs connected to their input section, digital on and off inputs, analog outputs, methods of programming the circuit using a PLC. So this is what we really wanted to touch on this week, was just like the analog side of stuff. So the input receives incoming signals, normally higher voltage, and converts them to lower power digital signals that are sent to the processor section. And then the processor registers and compares the incoming signals to the programs. So we're coming from the input going to the processor, and the input is normally higher voltage, okay? So remember that input, higher voltage, receives it and sends it to the processor section. Then the processor registers and compares the signals to the programs that it's programmed by. And then the output section receives the lower digital signals and converts them into high power signals. So it's coming in, that input is converting them to lower signals, sending them to the processor sends them back out to the output, and that normally converts them into higher power signals. Okay? Discrete inputs and outputs, they're the most common, and they use bits to represent a separate signal. So on and off, for example, like this bit's on, this bit's off, right? And examples of them would be push buttons, joysticks, relay contacts, temp switches, flow switches, etc. Discrete outputs, examples of them are going to be lights, relays, solenoids, starters, alarms, valves, motors, etc. Data, inputs and outputs, they produce or receive a variable signal, and they could be analog or digital. So analog versus digital, Analog has a continuous range of info going to it at all times. Digital is time separated. So it might have this bit coming in at this time and then 0.5 seconds later come in at this time. Analog uses ranges of values, whereas as digital uses discrete 0 and 1s to represent info. So we know that just from digital and PLCs and all that. You're going to use a 0 or 1 to represent information. And they are represented as sine waves, whereas digital is represented as square waves. And analog examples would be time sensors, FM radio, light sensors, etc. Digital examples would be computers, CDs, DVDs, etc. So, common input and output capacities would be mini-micro would be 32 or fewer, but up to 64. Small would be 64 to 128, but up to 256. Medium would be 256 to 512, but up to 1023, so 1023 inputs/outputs. Or large could be 1024 to 2048, but could be thousands. So all depending on the application you needed that PLC to perform is what you would spend money on. If you just needed it for a mini micro, you didn't need that many bits in there, then you wouldn't have to waste your money on buying a large, you know. But large would be mainly used in industrial applications, like what we was talking about, like in a plant or, you know, somewhere like that. That's where you would use a large one. And let's see. So now, this is where I got to. And then we'll get in the book here for a second. And this is a super long chapter, is why I didn't ask y'all to read it. It's like, I swear it's like 40 pages. Like it's crazy. Let me just see how many pages. I'm probably being over exaggerative, but it is a very long chapter. Like, super long. Let's just see. It is. It starts at 595 and don't end till 638. That's how long the chapter. It's a long chapter. So that's why I didn't ask y'all to read it. Alright, so we can talk about programming. PLCs, I know this is kind of bleeding into the PLC class, and PLCs is not my expertise, this is Robbie's, but it's because we're going to be doing that PLC lab combined with that motor controls lab this week. So like offline programming is the use of a PC to program a programmable controller that is not in the run mode. So this permits the computer to be used for other purposes when not being used for the programmable controller. So that's like the most common programming style is offline. So then we have different programming languages, and I know you know that from PLCs, like you're going to have run into different languages depending on the system that you're working on. So the first programmable controllers use line diagrams as a language to input information. So one type would be line diagrams. Alright. And they're still common. They're still commonly used as a language for programmable controllers throughout the world. So I would say they're the most common you're going to see. If you decide to go out in this field and, like, you know, work on PLCs or something, that's what you would run into 9 times out of 10, I would say. So other languages might include Boolean, which you're touching on that in digital, right? Start kind of learning about Boolean, functional blocks, an English statement. So let's see. Functional blocks in English statement are higher level languages, so required to execute more powerful operations. So let's say these two right here, higher level operations. Such as, let's see, data manipulation, diagnostics, and like report generation. So diagnostics. I know my handwriting is like the best ever. Reports. So if you needed to run diagnostics on a system, that's what those would be required to do. Like if you needed to see, is it performing to its utmost capabilities? That's what you would use. So a line diagram is drawn as a series of rungs. Each rung contains one or more inputs, and the output controlled by the inputs. So the rung relates to the machine or process controls. The programming instructions communicate the desired logic to the processor. So let's see. I'm not going to read all that to you. Okay. So the difference in programming is that although a circuit is the same, each manufacturer has a different method of entering that circuit. There are more similarities than differences from manufacturer to manufacturer. So different manufacturers equals different programming methods. So that would be like, you know, if you specialize in, let's say, Allen Bradley, they don't want their system to be the same as Siemens because you don't want to have a technician that could bounce back and forth between jobs or something. So I don't know, and it's just all a marketing thing. So different program specifications. Say that. Alright. Except for a few differences, programmable controller line diagrams are similar to standard hardware line diagrams. So the line diagrams we've already seen in this class. It all kind of is just like basically the same thing. So their line diagrams have two vertical power lines that represent L1 and L2. Except no voltage potential exists between the two lines. So horizontal lines represent the current pass between the vertical lines. Each rung may have several input and output devices. So you know exactly what I'm talking about when I'm saying ladder logic. Like that's all you did in PLCs. So like I said, Robbie's the master on that, so you should be good at what I'm talking about. And then input devices are either normally open or normally closed. You know that from PLCs. The normally open devices are referred to as examined if closed. And that stands for XIC. I'm sure you remember that too. And the NC devices, normally closed devices, are referred to as examined if open. So let me just write that down, just so it can give me a refresher too. So normally open equals XIC, which means examined if closed. And normally closed contacts, examine if open. All right. Let's see here. So just to go over a few programming rules. Let's see. So rule 1 would be, and this is basic controller circuit programming rules. The inputs, normally open, normally closed, and special, are placed on the left side of the circuit between the left rung and the output. So outputs are placed on the right side of the circuit, which you know that because it's easier to follow and stuff. Only one output can be placed on a rung. This means the outputs can be placed in parallel but never in series. So let me just write down rules for programming. So rule number 1, inputs on left, outputs on right. So rule number 2, only one output. Per rung. So outputs can be in parallel but never series. Alright. Moving on to 3. Inputs can be placed in series, parallel, or series dash parallel combinations. So inputs are a little bit easier. So inputs can be series, parallel, or a combo of the two. Alright, 4. Inputs can be programmed at multiple locations in the circuit. The same input can be programmed as NO and or NC at multiple locations. So inputs can be NO and dash or NC at multiple locations. So depending on the application that you're running, they could be normally open, they could be normally closed, they can be a combination of both. It's really cool. And then rule number 5, standard outputs cannot be programmed at multiple locations in the circuit. So outputs cannot be at multiple locations. I don't know if it helps you see me write it up there, but it helps me remember it if I write it down. All right. So just some examples of the rules. So like here's an example of rule 1. So you got your line 1 to line 2, and here's your rung. So then you would have your input and your output. So that's your I, O. And then, let's see, rule 2. Sorry, I was getting a call from a spam. Alright, so then let's see. So what do we say about our outputs? They could be in parallel, but they would never be in series, right? So we got our line 1 and our line 2. We got our rung right here. So this is rung 0. And this would be output 1. Then we have another one. Input, output. So then we would come down here, and we could not do this, right? That's not possible to do that. So we couldn't have 2 outputs on the same rung. Is it making sense so far? Just stop me if you have any questions, okay? I'm trying not to like bore you to death. Inputs can be placed, oh Lord, don't let me touch that. Inputs can be placed in series, parallel, or series dash parallel. So, like, here's an example of that. So we got our line 1, line 2. We got an input, an input, an input, and an output on rung 0. And that's in series, obviously. So then we would have this, an input, and then we would have another input, and then we would have another input. And that would be an example of parallel, right? All right. So let's see. So rule number 4. I'm gonna start a new page. So right around. So rule number 4. And this is probably gonna be on the test, but you can go back and rewatch these videos or whatever just to study. It'll be an open book test, so it should be an easy grade, okay? So rule number 4, inputs can be programmed at multiple locations in a circuit. So here's an example of that. You got your line 1, line 2, you got an input, and you got your output on rung 0. And now on rung 1, you have this normally open, then you have a normally closed, then you have a normally open, and then you have your output. And then you have a normally open, input, normally open, to your output. So that's just showing that you can have different kinds of inputs on the same rung in multiple locations in your logic. And then let's say rule 5. So standard outputs cannot be programmed at multiple locations in a circuit. So if you had line 1, line 2, you got input and you got output 1, and then you got input and you got output 2, and then you try to go down here. So you got input 1, and input 3, okay? Just wrap your head around that. And then you've got output 1, output 2, and this is just naming them whatever you want to name them. But you could not name this output 1 as well. So that's not possible. But you see how you can name your inputs 1 all the way down if you wanted to. All right. So a programming diagram is a line diagram that better matches the language of the programmable controller. So you're going to have to convert line. You're going to have to convert your line diagram to a programming diagram. And so it better matches the language of the program. Let's see. So let's draw an example of that. So, you know, a wiring diagram, we've went over wiring diagrams in motor controls. So you remember that, right? So this would be an example. Stop saying that. Why do you keep saying that? This would be an example of a programming diagram. Do you have any questions so far? We're going to do a recap here in a minute because I'm not going to overload you, okay? So, let's see. So you'd have your line 1 over here. Don't know why I put line I. And then, so then we would have a normally closed stop, a normally closed stop, a normally closed stop, normally closed overload relay. So stop, stop, stop. And then you would have your start right here is normally open. And then you would have your output. And that would be output 1. And then you would have your L2. So you would have another normally open start. You'd have another normally open start. So start, start. Nope, that one kind of crazy. Then you have a normally open. And this is 1, so that would be for your output. So obviously you see that when all that closes in, your output would become energized. So let's see. Oh no, I've probably got your brain hurting at this point. Sorry. Let's see. Alright. I just wanted to see this because this was a good question. Because it asked, what are the 4 basic sections of a PLC? So, we already talked about what happens whenever the higher voltage goes in the input, then it goes to the processor, then it goes to the output. So, when this question is asked, what are the 4 basic sections of a PLC? Your answer would be power supply. And remember this because it will be on the test. Power supply, processor, input section, and output section. Cool? Alright, so let's do a recap. I'm not going to overload you with too much more stuff. So, go back through here. So, the 3 different types of programmable controllers you might run into in the world would be PACs, PLCs, and PLRs. So, remember that, okay? So, programmable automation controller, programmable logic controller, or programmable logic relay. So, we're not going to touch back on that. That neither. So, what are some examples of systems PLCs might be used in? And that would be conveyor belts, traffic lights, elevators, roller coasters, wind turbines, car washes, etc. So just be thinking about like, wow, I'm seeing PLCs at work and not even realizing it. Discrete parts manufacturing. So makes durable goods such as cars, refrigerators, tractors, etc. So that's discrete. So just think more industrialized manufacturing is discrete manufacturing. Whereas process manufacturing is consumables such as food, gas, paint, paper, chemicals. And then let's see. So PLCs are primarily designed for the harsher environments found in industrial applications. So they can be expanded to control over thousands of inputs and outputs. So what type of manufacturing is a soft drink bottling plant?
It's not discrete, it's the
Process.
process.
And discrete parts manufacturing is like bigger things like cars and stuff like that. I'm gonna go back over all that. Alright, but we do need to know this. So the input receives the incoming signals in their normally higher voltage and converts them to lower power digital signals that are sent to the processor section. And then that processor registers and compares the incoming signals to whatever it's programmed. And then our output receives lower digital signals from the processor and converts them into higher power signals and sends them out to whatever output device that it needs to be sent out to. So, then discrete inputs, outputs, they're the most common. They use bits to represent a separate signal. Some examples of them are push buttons, joysticks, relay contacts, temp switches, flow switches, etc. Discrete outputs, examples would be lights, relays, solenoids, starters, alarms, etc. So line diagrams are the most common. And there's also Boolean, functional block, and English statement. And functional block and English statement are higher level operations. They're used in higher level operations such as data manipulation, diagnostics reports. Different manufacturers equals different programming specifications, like we talked about. So rules for programming: inputs on left, outputs on right. Only one output per rung. Outputs can be in parallel but never series. So remember that. Inputs can be in series, parallel, or a combo of the two. Inputs can be normally opened and or normally closed at multiple locations. Outputs cannot be programmed at multiple locations. And then we drew our examples. And then you're going to convert line diagrams to programming diagrams, and that way it better matches the language of the program. And that's an example of a programming diagram right there. And the four basic sections of a PLC: power supply, processor, input section, and output section. Okay? So if you forget any of this, you can go back and rewatch it on the YouTube channel. But I am going to have a quiz up. I'm going to start making quizzes every week now on stuff. So I'm also going to have a quiz up on variable frequency drives as well. So you might need to go back and rewatch that lab if you missed it. But other than that, that's really all we have to cover today. Do you have any questions or concerns, comments, whatever you might have? You sure? All right. Well, then we're good for now. Just keep an eye out on Canvas, and because there will be quizzes and stuff up eventually. Let me stop streaming this.